Assalamualaikum warahmatullahi wabarakatuh. Today, we would like to present our assignment entitled Mathematical Logic in AutoGate System. My name is Aisha Sofia binti Sazli and I presented together with my group members Nur Ain Amalina binti Wan Muhammad Asri and Nurul Damia binti Azman. This presentation will explain how mathematical logic is applied in an AutoGate system using logical connectives and truth tables. So for today, we will be explaining about what is mathematical logic, why we use mathematical logic, case study, logical connective, problem solving, and the summary of our project. Mathematical logic is a branch of mathematics that focuses on logical reasoning. It helps us determine whether a statement is true or false by using symbols and logical rules. Mathematical logic is commonly used in computer systems, engineering, and decision-making processes. Why we use mathematical logic? We use mathematical logic because it helps us to think clearly and systematically. It also improves decision making and helps solve problems in an organized way. In real life, logic is used in technology, programming, and automated systems such as AutoGates.
Now, let's look at our case study. So, our automated machine is designed to control vehicles for home and commercial buildings. The goal here is efficiency and safety. So, the system is operated based on two primary inputs. First input is the remote control used by the owner to trigger the opening process. And input B is the safety sensor which detects obstacles like cars or pedestrians to prevent accidents. So, by applying logic connective and truth table, we can program the system to decide exactly when the gate motor should move, stay stopped, or trigger an alarm. Before we look at the circuitry, let's look at the operational logic. So, we have four main states. First is 00, power off, no remote signal and system is idle. 01, stop, again, no remote signal but the sensor might be triggered, the gate remains stationary. 10 is standby, the sensor is clear but the remote hasn't been pressed, the gate remains closed and ready. 11 is open, this is our true state for movement. The remote is pressed and the sensor is clear, allowing gate to open safely. Now, let's break down the truth table for our three outputs, move, stop, and alarm. When both inputs are true, meaning the remote is pressed and the sensor is clear, the gate moves. If the sensor detects an obstacle, false, the system is programmed to stop and trigger the alarm to alert the user. Essentially, the move command only activates if specific logical window to ensure there is never a collision. So this is our logic circuit diagram. It is to visualize the flow of AutoGate system. So on the left, we have our input, remote and safety sensor. This signal enter the logic circuit which act as the brain of the gate. Based on the Boolean logic we have established, the circuit sends a signal to one of the three hardware components, the motor gate to move the gate, the stop mechanism to freeze it, or the warning light or alarm for safety alerts.
Logical connective. In our project, we use a truth table to ensure that our mathematical equation match the actual behavior of the gate. And here we use different logical symbols like conjunction, disjunction, negation, conditional, and biconditional. It is to show how the system thinks and stays safe. For example, we use the formula of A and B is equivalent to M, which means that the gate will only move M if the user presses the remote A and the sensor B is clear at the same time. And if the sensor sees an object, the condition becomes false and the gate will stop to prevent an accident. So by using these logical rules, it helps us prove that the AutoGate is reliable and works correctly every time. Logical connective. Next, to understand our system brain, we must look at the specific connective that we use. So first, we utilize conjunction, which means and it is represented by the heat symbol. Second is disjunctions, means OR. It is represented by the val symbol. Thirdly is for not statement. We use negation known as tilde. And next is our logical flow is tied together by the conditional if then, and it is represented by the arrow symbol. And the last one is be conditional. It is if and only if we use the double arrow symbol. So these symbols actually allow us to translate physical safety requirements into physical certainties. To define the specific operational state of our auto gate, we have developed 4 distinct logical formula that govern the system behavior. So first, we use the formula of A and B is equivalent to M. So it is explains that the gate moving M is logically equivalent to the activation of either input A or B. Second, for more complex safety switching, we utilize the expression of A and not B or not A and B is equivalent to S. So this state the condition is met only when A is true while B is false or vice versa. Thirdly is the formula of A and not B is equivalent to L. It defines that which occurs specifically when input A is active and B is negated. So finally is not A and not B is equivalent to O. It is represent the idle or open state O, which is logically equivalent to both input A and B is being inactive. So now let's proceed with problem solving. So the first problem solving is A and B is equivalent to M. And here we do have 4 columns, and the first one is A, which is true, true, false, false. Second one is B, true, false, true, false. Next is A and B, true, false, false, false. So the conclusion is, since all true values in column 3 is equal to column 4, therefore A and B is equivalent to M. Next problem solving is A and not B or not A and B is equivalent to S. So and here we have 8 columns, and the first column is A, which is true, true, false, false. Second B, true, false, true, false. Next not A, false, false, true, true. Not B, false, true, false, true. A and not B, false, true, false, false. Not A and B, false, false, true, false. A and not B or not A and B, false, true, true, false. And the conclusion is, since all true values in column 7 and column 8 is equal, therefore A and not B or not A and B is equivalent to S.
Next, I focus on problem solving 3, which is A and not B equivalent to L, which L is alarm. For A, we have true, true, false, false. For B, true, false, true, false. Not B, false, true, false, true. A and not B, false, true, false, false. And L, false, true, false, false. So, for the conclusion, since all true values in column 4 equal to column 5, therefore A and not B equivalent to L.
For the next problem solving is to ensure our system fails safely. So we also analyze the inverse logic. Let's look at the expression not A and not B if only and if O. So this helps us define what happens when the system is off. As you can see in the truth table, if both the remote A and the sensor B are not sending a signal false, the result for the off state becomes true. This confirms that our logic holds up even the system is inactive, ensuring no-go signals trigger the gate unexpectedly. So in conclusion, by using simple logic rules, we built a gate that is not just automatic, it's safe and smart. It knows when to go, when to stop, and when to warn us. It's a great example of how technology uses math to make our life just a little bit easier and a lot safer. Thanks for listening and bye.